Hello, I didn't see you there. Today we're going to be doing our carbonate and bicarbonate analysis, and that involves a couple of different titrations. The first one's a fairly simple, just hydrochloric acid titration. The second one is a little bit more complicated because it involves doing a back titration. So I'll get started on showing you the procedure for that, and then we'll talk about why it works. So to start our titration on these water samples, the first thing we need to do is get the water into our Erlenmeyer flasks. I said before that we have to do 2 titrations for each sample, but each of those titrations we have to do in triplicate. So each sample that comes in for a carbonate or bicarbonate analysis is actually going to have 6 total titrations done on it. So we're going to need to fill up 6 different Erlenmeyer flasks. Each of those are going to take 25 milliliters of our water sample. So we have a couple of ways that we can do that. Our first are with these volumetric pipettes. We have a 20 and a 5. And then the second would be with our mechanical pipettes. And that would be using the 10 twice and then the 5 once. Ideally, we would be able to do it in one single aliquot to reduce our error, but with what we have to do at least 2, and probably 3, because these are a lot easier to use than our glass pipettes. So to get our 25 milliliters into our Erlenmeyer flasks, I first want to demonstrate how to use a glass pipette. We're going to use our 20 and then also our 5. So the first thing you want to do is hold the glass pipette near the top with your dominant hand and your pipette bulb with your non-dominant hand. This might feel unnatural at first, but you'll see in a bit why you want to do that. So just insert the tip into your sample, squeeze your pipette bulb, put it on the end there, and you can start to suction up the liquid into this volumetric pipette. You don't want to go too fast near the top because it goes pretty quick. And then when you get near the top, you want to pull that bulb off and then quickly cap the top with your thumb. And that's why you want to be using your dominant hand for this, because your dominant hand will be a little bit stronger, have a tighter seal on the top there. And so now, let's see if I can bring this in. Our sample, we want to get it to that line. It's a little bit above, so I'm just going to very slowly release some of the pressure until the water level goes down to where that line is. Now you might be able to see it coming down. And then when it gets down to that line, remember you always want to measure at the bottom of the meniscus. Try and get that bottom of the meniscus to match up with that line as closely as you can. See, like that. And then hold it over your Erlenmeyer flask and just let go. It's going to take a few seconds to flow all the way out. And then when it does, it's going to leave a little bit of volume in the very tip. That's okay, you want to leave that there, you don't want to blow that out. These volumetric pipettes are designed so that whatever flows from that line out just by gravity is the volume that you want. So you can see right there, there is a little bit of water left in the tip. That is okay, we want to leave that. So we put 20 into that first one. We need to do 5, and it's going to be the same method. So here, holding the 5 volumetric pipette in my dominant hand, squeezing the bulb with my non-dominant hand, put it on top, and suctioning up about 5 milliliters. And again, I'm going to try to release the pressure to bring the volume down to that line. Measuring at the bottom of the meniscus. Tightening up the pressure, bringing it over to my Erlenmeyer flask, and just letting go. And this is a laboratory skill that takes a bit of practice, but conceptually, it's not too difficult. I'm going to let this run out and then do the rest with our mechanical auto pipetters. Okay, you see there's still a little bit left in the tip. That's what we want. Okay, so now we're going to use our auto pipetters. We're going to use our 10 milliliter twice and our 5 milliliter once. We want to make sure that that is set to 10. That's at 10. And then I want this one to be set to 5. Always make sure you check to see that you are actually delivering the amount that you say you are. Okay. We have our tips over here. You'll want to use a different tip for every sample, but since this is the same sample going into now 5 different Erlenmeyer flasks, it'll be okay to reuse this one over and over for this analysis. So when you have one of these in your hand, there's this plunger at the top. It has 2 stops. If you push it down, there's like a soft stop, and you can push it a little bit further till you hit a hard stop. What you want for the suction is to hit the soft stop and then pull all the liquid up from there. So I'm going to push it down until it gets to that first soft stop, put it in, suction up the water that I want. With these tips, it's sometimes good to do this a couple of times to prime it, just to get a little bit wet at first. So I'll do that again. Put it all out. And this will be the real one. So again, this plunger is going to be down at the first soft stop. I'm going to pull my liquid up from there. You want to do that a little bit slowly. And then when you put it over your container that you want to deliver to, that's when you push it down to the hard stop. Because if you go down just to the soft stop, you're going to leave a little bit in the tip. And these are different from the glass pipettes, where you want to get all of that out. So now there's a little left in that tip. I'm going to push down to the hard stop to get the rest out of there. I'll do that again. So that was 10 twice. That brings us to 20. So then we can get our 5. The 5 has a different tip on it, but again, I'll save this tip throughout. Going to do a little bit of priming. Just 2 to 3 is all it needs. Alright, and then pushing the plunger down to the soft stop, putting it in the water, slowly pulling it back up, and then putting it into my Erlenmeyer, pushing it down all the way to the hard stop. That's it. I'll probably do the rest on fast forward, so you don't have to sit through me doing this 4 more times. Okay, so those are done. One thing I think I mentioned before is that under ideal circumstances, we would be doing this just in a single aliquot. And the reason for that is every time you make a delivery, you're introducing some amount of error. So with our glass pipettes, we're doing that twice. We're introducing error 2 separate times, once with the 20 and once with the 5. With our mechanical pipettes, we're introducing error 3 times, twice with the 10 and once with the 5. So Under ideal circumstances, we would just have a 25 milliliter pipette, and we would do that and only introduce the air once. But that said, just because of the speed and ease of use, we tend toward mechanical pipettes. So here we are with our titration setup. We have our standardized hydrochloric acid that is standardized to N/50 or 0.02 normal. We need to make sure we use standardized hydrochloric, or we make our own hydrochloric and then we standardize it. That takes a lot more work, so we just buy it. The reason for that is we need to be making sure that we're putting in a really precise known concentration of our hydrochloric acid into our solutions. We also have our squirt bottle of deionized water and a little beaker to hold our hydrochloric acid, and then our buret setup. I don't think I can get the whole thing in frame at once, so I might have to do some moving of the camera for this. But so I'm just going to start by filling up the beaker with my hydrochloric acid and then using that to fill up my buret. This is only a 10 milliliter buret, so we don't have to have very much. We are going to fill it and drain it a couple of times, and you'll see why. You want to be careful filling this because it's got a very narrow neck, so you have to fill it slowly, and we don't even have a funnel that is skinny enough to fit in it. If you do spill, like I just did, then you're going to want to wipe it out before you start your analysis so that none of those stray drops get into your solution and interfere with your results. I'm not sure if you can see from that distance, but I'm getting near the top. I actually want to fill up over the line because I am going to come down to the stopcock down here and let some drain through. I might actually go free camera mode so you can see what's going on here. So down in here there's still air because we haven't let anything flow through. So if we turn this down, you'll see it start to flow, and then I don't know if you caught that, there was a little bubble that came out, and that's what you want to get. There's typically going to be some trapped air in there, and sometimes it will get stuck right around this area, so you might have to let it flow, turn it off, let it flow, turn it off. Just make sure that you get that bubble out, because if you don't, then that's going to give you an incorrect volume measurement if it does eventually come out when you're running your analysis. And so now I have used up more than I really wanted to, because it's much below the zero. We want to start at this zero line. So in the same way as our volumetric pipettes, we're gonna fill to above the line and then drain down such that the bottom of the meniscus is right there on that zero line. Let's see if I can do this while holding the camera. Again, very slowly. Okay, so I'm above my zero line. Let's see if that's in frame. I can't really tell. And then I'm going to slowly let the liquid out the bottom until that bottom of the meniscus is at the zero line. There we go. You want to make sure you're reading this straight on. I have it right about at my eye level, so I don't have to stand up on my tiptoes or crouch down or anything. You can adjust the height of this buret clamp in order to help you do that, or just adjust the height of the buret on the clamp. Just makes it easier if it's already at your eye level, so you don't have to stoop or anything. The indicator we're going to use for this first titration is bromocresol green. The funny thing about this indicator is that in an alcohol solution it is orange, and when we put it in the water it's going to be yellow, I believe. Let's see. Oh no, it's blue, and then it's going to titrate to a yellow. And so you may be wondering, if it's orange in our alcohol solution and it's blue in basic water and it's yellow in acidic water, then why is it called bromocresol green? And the reason for that is that in that very thin endpoint between the blue and the yellow, they say it looks green. I don't really see it. I think that they're just expecting green because they know it's between blue and yellow, but it's really tough to find it in a green state. So we put a couple of drops of our bromocresol green into each of these, and now we're just going to titrate to that yellow endpoint that I mentioned. So our first titration, you're going to want to go pretty slowly because you don't know where this is going to be. So I'm just going to go dropwise to start, and probably fast forward this until it gets near where it needs to be. You can see I'm swirling this. I tend to just do this by hand. We could have a setup where we have a magnetic stir bar stirring it automatically, but I find that to be as much of a hassle as it is a help. I actually didn't have to fast forward because there wasn't a whole lot in there. So you can see that yellow endpoint compared to the blue where it started. This is what we're looking for. And so now we need to record our volume used. I'm gonna go free camera again. Hopefully this is in frame. One thing when reading volumes on a scale like this, and this is the same for graduated cylinders or for more pipettes, anything with these markings, is you always want to estimate one step further than what you can see marked. And so right now we have our 1 line here, our 2 line there, and I think there's actually 20 gradations in between. But so that's our 1.1, 1.2, 1.3, 1.4, 1.5. So it is just about on our 1.4. I would say it's not quite there, and so we may actually call that 1.39, or somebody else could say that's a 1.40. But the main takeaway is that you're going 1 decimal place further than what you see. You're not just going to report that as 1.4, you're going to report it as 1.40 or 1.39. Okay, so I've refilled my buret back up to the 0 line off camera, and I'm just going to continue these titrations in fast forward now. Okay, so I've done all 3 now. I think that last one is about 1.33, so we're going to write that down and get started on the next part. Okay, so this second part of the analysis requires a few more reagents and pieces of equipment. I have gotten out a 10 milliliter graduated cylinder and my 1 milliliter mechanical pipette set to 0.4 milliliters. Set this aside for now. We need our 10% barium chloride solution, which we keep right here at the titration station. That's also where we keep the bromocresol green and our phenolphthalein indicator, which we're going to be using now. So
this part, there is a kinetic aspect to it, so we can't prep all of them and then titrate all of them. We are going to have to do one prep, one titration, and then move on. Second prep, second titration, third prep, third titration. So what the prep is, it's only a little bit more complex than what we just did, but we need to take 0.4 milliliters of our standardized sodium hydroxide solution. This is standardized at 0.25 normal. That's why we need so very little of it. And just the same as before, I'm going to prime that a few times. And then pull up my 0.4 milliliters and plunge that down into our first Erlenmeyer flask. Next, I want to swirl that a little bit, and then I want to add 10 milliliters of our 10% barium chloride solution. I'm going to measure this out, and this one does not have to be exact. The barium is being added in excess, so you want about 10 milliliters, but don't sweat too much on the volume on that. So we're going to pour that into our Erlenmeyer flask, and what we often see, but not always, is you're going to see a cloudy white precipitate in there. I'm not sure if it'll show up on the screen, but it actually is in there from what I can see. So if you want to compare the clear versus the cloudy, we have got some precipitate in there. Now we want to add a few drops of phenolphthalein. You don't need much, as you'll see. Phenolphthalein is famously a bright pink color, so 1 to 2 drops is really all you need. Swirl that around a little bit. All right, and then we're ready to titrate. And this titration from here on is going to work just like the last one, except instead of going from blue to yellow, we're going to be going from pink to non-colored, just a clear, cloudy, uncolored solution. Again, for the first one, I'm going to start pretty slow, and if this ends up needing a higher volume, what you can do for your subsequent titrations is get close to the volume that you want and then go slow. So for instance, if I do this really slowly and it turns out I'm going to need 8 milliliters of hydrochloric acid titrant, I will, for the next ones, use about 6 milliliters just really quickly and then slow it down and go dropwise from there. So as I don't know how long this is going to take, we may or may not fast forward this part. I don't know if you can tell, it's starting to get lighter, so I'm going to slow the dropping down even further. We're getting close to the end. There's still a little bit of pink. I'm going to say that is about cleared up of all of its pink color. So we can stop the titration there and record our volume, which I am reading at about 2.70 is what I would call that. Just gonna take a second to write this down, and I'm gonna continue on with the other 2 titrations, and we'll definitely fast forward these next bits. Once again, I have spilled the hydrochloric acid because this buret is so skinny. Patience is key with titrations, and that includes all aspects of it. This aspect requires not only patience, but also a bit of dexterity. But as with anything in the lab, with practice, you can get good at it. Okay, got it down to the 0 line. Going to add in 0.4 milliliters of my sodium hydroxide. And 10 milliliters of my barium chloride. Swirl it for about a minute until you see some cloudiness. Maybe less than a minute. Add 1 to 2 drops of phenolphthalein and titrate. So like I said before, I can go a little bit faster now. I read about 2.70, so I'm gonna go fast to about 1.5 and then go slow, and this will save me a little bit of time. You just don't want to overshoot it, or else you'll have to do the entire titration over. Just that one, anyway. Okay, I am gonna call that done. So that looked like, ooh, that's closer to 3.06, I would say. Just write that down for a second. And we are ready to do our data analysis. Actually, before we do our data analysis, there's one important step that I almost forgot, and that is cleanup. So we have now kind of a big mess in front of us. We've got our barium chloride. That's okay, that stays in its sealed container and that just goes up on the shelf here. We have our graduated cylinder, and that could just go to soak in our detergent solution. We have our hydrochloric acid. This will go back into our acid cabinet. And then just about everything else is going to go into acid waste. So we have the beaker we were using to pour hydrochloric acid into the buret. We have the hydrochloric acid that is still in the buret. I'm actually going to drain that now into our waste beaker. So dump that in the waste beaker. We have our 6 Erlenmeyer flasks, which have all been titrated with hydrochloric acid, so they should be more on the acidic side. Just to be safe, we're going to put those into acid waste. The only other thing is our standardized sodium hydroxide, which is going to go into base waste. Once this buret is done draining down, I'm going to take my deionized water and put a little bit down through my buret, make sure it is rinsed all the way out. I will even probably fill it up to the top, let that rinse down, fill it up again, let it rinse down, and then just let it air dry from there.
Okay, so we have our Excel template here, and it's pretty easy to use. It does all the calculations for you. So right now I'm just going to put in the data that we gathered today, and then later on we will explain what it's doing, how it's doing it, and we'll come back to this Excel spreadsheet. But so right now we just have our sample ID 191023039. You'll see when we hit enter on that, it'll automatically populate down here. And then we want to enter our 3 volumes of hydrochloric acid used from our first titration. So that was 1.39, 1.34, and 1.33. You can see it populates the calculations over here from that information. And then we just need to enter our volumes from our second titration. So that was 2.70, 2.84, and 3.06. So once you've entered all of that in, it populates all of this, and what you want to report are these highlighted cells. So milligrams per liter of bicarbonate, we would report 104. Milligrams per liter of carbonate, you see it has a negative number. While that doesn't really make sense, that happens just because we're working with such small amounts, and so we would report this as a non-detect. So now we're going to transition over to the theory behind this, but what you've seen so far is enough for you to get started and reporting some data.
Okay, so what is going on with this carbonate analysis? Well, it's gonna have you reaching back to high school chemistry or freshman chemistry with what's happening inside the solution there, but if you think it through, it all sort of makes sense. So we have in our solution some unknown amount of carbonates, and that counts as regular carbonate, CO3 2-, and bicarbonate, HCO3 1-. Those are also going to have counter ions, right? Probably sodium, but we really don't care about our metals in this case. All we care about are our carbonates. So you have this solution, you have an unknown amount of bicarbonate, you have an unknown amount of carbonate, and our first titration is how we determine our total carbonate. And so we're adding in hydrochloric acid, which gives us our proton, right? This dissociates into H+ ions and Cl- ions, and just like the sodiums, we don't really care about the chlorides. So we're just going to be worrying about the interaction between our hydrogen ions and our carbonate and bicarbonate ions. So those two reactions are hydrogen plus carbonate is going to net us carbonic acid, H2CO3. And of course, to balance this equation, we need a 2 in front of our hydrogen. So we have 2 hydrogens to start, 2 hydrogens to end, and then a carbonate to start and a carbonate to end. So that's one of our equations. The other one is H+ plus HCO3 also yields carbonic acid, H2CO3. So assuming these are the only counter ions in the solution that are going to interact with our hydrogen ions, then we can tell by the amount of HCl we put in how many of these hydrogen ions were used up. That said, we don't know the split between them, right? If it was a solution that has a lot of carbonate and not a lot of bicarbonate, that would take the same amount of HCl as a solution that has a lot of bicarbonate and not a lot of carbonate, assuming, you know, the same concentrations but flipped. And so this is only the first piece of our puzzle. The second piece comes from that second titration. So if you remember, the first thing we did in there was add an amount of sodium hydroxide. And so what that's going to do is, if we have carbonate, CO3 2-, and we add in hydroxide, OH-, that's not going to do anything. That's going to stay CO3 2- and hydroxide. So no reaction there. But if we add in hydroxide to a bicarbonate, so HCO3 plus OH minus. That is going to strip this hydrogen off to convert this to a water and a carbonate. And so now we have CO3 2 minus plus H2O. And the whole thing is in water, so this we can kind of ignore. So that first step of putting in sodium hydroxide was done to convert any bicarbonate to carbonate. The next step was the barium chloride. And what's happening there, we have barium chloride, BaCl2, plus our carbonate, because now there are no hydrogen carbonates, no bicarbonates. So CO3 2 minus. That is going to react and form barium carbonate, BaCO3 plus 2 chlorides. As before, we don't care about the chloride. The noteworthy thing about this barium carbonate is that while everything up here is aqueous, this is a solid. That is our precipitate. So what we've done is we have now pulled all of the carbonate out of that solution, right? We started with some unknown amount of carbonate and bicarbonate. We added the sodium hydroxide to convert it all to carbonate, and then we added the barium to hook up with that carbonate and make it a non-issue. So now floating around in solution, we have none of the carbonate that we started with. What we do have, though, is leftover hydroxide ion. And so, switching to a new paper. And so what we're actually titrating against is that leftover hydroxide. And so that's why it's important to use a standardized hydroxide solution, because we need to know the exact concentration of that. And then the titration is pretty simple. We have our hydroxide that's left over from converting the bicarbonate to carbonate. We're adding in hydrochloric acid, and then that's going to be titrating to water and chloride ion. And once all of that hydroxide is used up, that's when we transition from that bright pink color to the clear, colorless solution. And that's when we know we've spent all of that. And so we're measuring how much HCl that we put in, but that's going to tell us how much hydroxide there was in solution. And by knowing how much hydroxide there was in solution, subtracted from how much we put in to start, we can then calculate how much bicarbonate was in solution. And then if we know how much bicarbonate was in solution, we can take that and subtract that from the total carbonates that we determined from the first titration and find our carbonate in solution. So what we've done is called a back titration. We've put something in to react with what we care about and then titrate it against what's left of what we put in. And so we have to do some more calculations backward in order to determine how much was there to begin with. I think we're going to switch back to the Excel spreadsheet now, and then you can see those calculations happening in real time on the Excel.
So we're back here at the Excel spreadsheet. This is all the data that we had previously entered. And now we're just going to take a look at each of these cells and see what calculations they're doing to try and understand how we're getting to these final answers. So keep an eye up on the formula bar really up here as I'm tabbing through to see what these are doing. So average volume for that first titration, that's pretty easy. That's just taking the average of B2 to B4. So adding those up, dividing by 3, get the average. Simple. The moles of total carbonates here is now taking that average, C2, multiplying it by 0.02. That was our concentration of hydrochloric acid. And then dividing it by 1,000. That's just a factor converting from milliliters to liters. our molarity of total carbonates is now taking that value that we calculated and dividing it by 0.025. That was our initial volume of sample. So we had 25 milliliters of sample divided by that to get our concentration in molarity. So that is our concentration and molarity of total carbonates. If we come down here, we have average volume again for the second titration, so that's doing the same thing, just averaging these three. And then in this column I have now written moles of HCl used. That really is the same as what was going on in this column. I just did a quick conversion because in that case they were the same. But so moles of hydrochloric acid used is going to be our average volume multiplied by the concentration of our hydrochloric acid. With that, we can go over to the moles of bicarbonate. So you can see this is taking B11 and then subtracting out our D7. Our B11 is our initial moles of sodium hydroxide. This I have just as a constant in this Excel spreadsheet because we're always putting in 0.4 milliliters of the 0.25 normal sodium hydroxide solution. So that's where that number comes from. So right here we are subtracting our initial moles of sodium hydroxide minus the moles of HCl used, and that will tell us how much of the sodium hydroxide was used by the bicarbonate ions in converting them to carbonate. This cell is just a D2 minus E7, so that is taking this cell up here, the moles of total carbonates, and subtracting that cell. So we know from here the moles of bicarbonate, we know from up here the moles of total carbonate, and we're subtracting that to find the moles of just the carbonate ion. So really when we have these two, we have some form of the two answers we're looking for. However, we don't report in moles, and most people wouldn't understand what that means, so we have to convert to something that they do understand. So this cell and this cell are both similar. They're just converting from moles to grams. Of course, you do that by using the molecular weight. So we have the molecular weight of bicarbonate down here as a constant and the molecular weight of carbonate down here as a constant. And we're just taking the moles of each of these and multiplying it by the molecular weights to get the mass in grams. And then finally, to go from grams to the concentration that we report in milligrams per liter, we have to take our grams and then divide it by our initial volume, that was the 0.025 liters, and also converting from grams to milligrams we have to multiply by 1,000. So this cell is just taking the cell next to it, multiplying it by 1,000, dividing it by 0.025, and that's how we get our 104. And then this cell is taking the cell next to it, doing the same thing, but since we started with a negative mass here, it's giving us a negative concentration. Again, that doesn't make sense in the physical world, so we call that a non-detect. Anyway, that should be it for today's video. I hope you learned something. Make sure to check back later.